Hello everyone, welcome to my channel. This is Dr. Vijay. Today we will learn common source amplifier with diode connected using 180 nanometer technology node. In my previous video, we have already designed common source amplifier with resistive load. So same circuit we have taken here to implement diode connected. The only difference here is the resistor of 318 ohm will replace with NMOS gate connected to VDD. Now you can observe that the transistor NM2 width has been considered as 2 micro to perform dummy DC analysis. After performing the dummy DC analysis, we can easily identify the region of operation of the transistor. So this NM2 transistor should be in saturation region along with NM1 and NM0. So to perform this only we have right now considered W equal to 2 micro. Now we'll check uh, the DC analysis while going into launch. Let's go and then ADEL. Here you click DC and then after you click DC operating point and just run the simulation. Once you run the simulation and after finishing the simulation you will observe that parameters nearby transistors. So in order to check each transistor region of operation, we have to again go here under result, then print DC operating point. Just click the transistor and one window will pop up. Here you have to search region. If region equal to 1 means it is a linear, if region equal to 2 means it is a saturation. So you can observe over here this transistor region is 1, that means it is under linear region because of this width that we have considered randomly equal to 2 micro. And similarly this transistor that we have at NM2 is in saturation and NM1 is also in saturation, but due to this width of NM2 this NM0 transistor is in linear region. So we have to identify an optimum width such that all the transistor will be in saturation region, right? To identify this, we have to perform parametric analysis. To perform the parametric analysis, this transistor property we have to open and we have to keep a variable. That means the width that we have considered 2 micrometer that we are going to replace with variable capital W and then press OK. If you want you can make these fingers 5 so that more width you can add over here, otherwise it will give error. Now again go to analysis and find out what are the variables you have in your circuitry. Right now we have only single variable that we are initial value we are giving as a 2 micro. Then after once you have given this width equal to 2 micro, we have to go with region of operation. For that you just click setting output, then open the calculator here such that we can place the expression over here. Once you open the calculator, click OPT, that is operating point, and then select the required transistor that you want to identify the region. So this NM0 is in linear, so we have to make it in saturation region. For that, in the drop down menu you identify where is the region. Search carefully because lot of parameters are given over here, so be careful. Yeah, right. So region you once select, it will show operating point, then within the bracket NM0 and the region. This you can directly copy also if you want. If you want to copy it, you simply copy it, otherwise you can directly go into that and from there click again setting option. Yeah, here just click get expression and give the name of this. So I am giving region of operation ROO and click get operation. Once you click get operation, same syntax will get over there and then you add it into the table, then press OK, like we are selecting the terminal. If you want, you can close it also, no issue. So here you can see that initial value 2 micro is already there, so we have to go into tools, parametric analysis, and then you from the drop down menu you search W, that variable. So give the initial value, you can start from 2 micro to 15 micro, that you can type it here. Then after the step mode, that you can give linear steps. Once you have given linear steps, you make it 1 micro, so every 1 micro it will iterate. So now you have to wait till it will go up to 100%. Once 100% it will finish, then after one window will get generated. There you will see one waveform, and you can observe at what particular width this transistor is becoming saturation. So you can observe here also running status. So now you can observe over here this waveform, and if you move your cursor around this region, you will identify approximately 13 micro. So approximately 13 micro, our transistor will be in saturation region. So minimum this much width we have to provide in our circuit. So again we can close this circuitry. This also we can close, just minimize it, and then you replace this thing. So right now we have given unknown parameter W, and that we identified, right? So this transistor property you have to open and just replace this with 13 micro, and then press OK. So now this is the transistor width that make all the transistor in saturation region. Again we will do a small dummy analysis so that we can identify whether all transistors are in saturation or not. For that this design variable no longer needed, because we don't have any unknown variable. Again you simply run those things, and then again we have the same process. Click on result, then print DC operating point, and click one by one all the transistors. First we'll check NM0, and we'll see its region of operation should be 2, right? Previously it was 1. So now you can observe that region of operation it is showing 2. Okay, we'll cross verify other two transistor also. So NM2 transistor is also region of operation 2, very good. And this NM1 is also region of operation 2. So all transistor is now. So this is the optimized width that required for diode connected load, right? Now after this we have to perform AC analysis. Just simply click AC, then give frequency from 1 to 1 gigahertz. Okay. Oh, small g, please don't keep small g, keep it capital. It is case sensitive, so make it capital G, and then press OK. Yeah, uncheck which you don't require, and then after you simply run it like we did in the previous video. If you have not gone through my previous video, please check common source amplifier with resistive load, there you will get. Then after again go into the result, then direct plot, then main form. Okay, click on the main form. So here make it sure that the function should be voltage, and then 20 dB, and then it is saying select an input. So output we are selecting, as in the input we have given a magnitude of 1 volt, so V out by Vi, it will directly give the output. So here you can observe that the dB that we have over here, or you can press H to get this line. Okay, so accurate point, if you want you can just hold it here. Yeah, 10.6275 dB, right? So if you want 3 dB, minus 3 dB value at what frequency we are getting, then you can again press H and just minus 10.66 you have, so do it 10.66 minus 3 dB, so it will come 7.66 something, yeah, dB. So this is our 3 dB frequency. So if you check, it is around 107.64 megahertz. You can also check 0 dB also, means unity. So if you select 0 dB, you can observe the frequency for this also. So frequency for this is around 336 megahertz. If you click this line, then also you can get it. No issue. 339.298. Similarly, you can select the other line also. Once you select, it will reflect automatically, right? So this is what you have observed. So our requirement was 13.98, but we are getting this much, right? If you want, you can change the color also. Close it. If you want to cross verify in the magnitude level, that also you can do and check how much you are getting. It is approximately 3.4, right? You can increase the width also. Yeah, so 3.412. It is in linear mode, not in dB, right? Now you can also go for one more analysis if you want to check how much amplified version of signal you have. So click transient analysis and go for 10 milli, because we have given frequency of 1 kilohertz, and then select input terminal and the output terminal, and then simulate. Just click that green symbol and you will see the two waveform. Yeah, so separate it. Yeah, now you can see we have a two waveform, and if you want, you can identify the peak to peak voltage of input waveform and output waveform. For that, you simply click the waveform and then select calculator. Then after, click here peak to peak. Click peak to peak. Once you click, then you calculate it. Yeah. So 1.989 in 10 to the power minus 6. So 1.989 milli. So we have given 1 milli, that is for input. So if you take peak to peak, it will become 2 milli, right? So again, similarly, you have to do for the output also, and you check, it is around 6.792. So from 2 milli to 6.92 milli, right? And that you can check with the gain that we identified, 3.42, right? That you multiply, you will get the same thing, correct? Thank you.